Hi viewers, so before watching this video please subscribe it. Don't forget sharing to your friends also. So now topic is potential energy of the system of charges. Okay, so potential energy of system of charges. Here system of charges means more than two charges present. So anything more than two bodies is called system. So that is why potential energy of, instead of potential energy of charges, heading is written as potential energy of system of charges. Okay friends, system means two or more than two bodies or charges. Okay, now consider a system of two charges q1 and q2 separated by a distance r1 as shown in figure. So in the figure is shown how many charges are there? Two charges are there and they are separated at a distance r. Okay, now see the diagram. So it is first charge, second charge, and these two charges are separated at a distance r1. R sometime it is also called as r. So when it is not moving it is r. When the charges are in motion then r1. After motion charges distance is r2. So that is why here three distance are given. This r is when no change in the position of charges, and this R2 R1s are when the change in position of charges. So that is why when the position changes, distance also changes. Okay, now next, the charge q1 is fixed. See, this charge is fixed at a point a. At a point a, let the charge q2 be taken from position B to position C along the line ABC. Here charge q1 is fixed, but q2 is what we are doing. Now q1 is at a position A, q2 is at a position B it is. Now what we have to do, we have to move it from B to C. Okay, then what happens, in the previous position distance is r1. When it is changed to the position C, its distance is r2. Let AC and C, they moved in the direction of ABC. ABC along the line ABC. So that is why ABC is written. Let AC means A to C distance. AC distance r2. Consider a small displacement of charge q2 from a distance r2 r plus dr between B and C. Initially I said you either r or r1 both are same. When it is changed from here to here, let the small distance is moved. That small distance is, let me take it as write as r plus dr. Okay, between B and C, that is electric force on the charge q2. Sorry, right. Okay, when two charges present, then electrostatic force will create. Okay, the electric force on the charge q2 at a position B is, it is a force between the two charges, that is F is equals to 1 by 4 pi epsilon naught q1 q2 by r square. Let it is equation 1. Now work done by this force for a small displacement dr. So we know the work done, work formula, work is equals to force into displacement. So work for the small distance, work is also small. So that is why dw is written. If you write w as work, then dw is also work but small work. Why? Because small distance is changed. If the more distance is moved, then work is also more. Okay. On integrating above equation from R1 to R2, from this position to this position, then we get total work done we get. So if we integrate on either side, what happens here? Integration differentiation cancel, so w will, we will get here w, right? Once again, when you integrate on either side, here integration differentiation cancel, but here integration differentiation never cancel. Why? Because in between them f is there, that is the reason. But this side no one will present, so that is why directly integration differentiation gets cancelled. Okay, and here this side integration is where to where, from r1 to r2 f dr, and f value we know, take and substitute here. See the next page. Yes, f value substituted from equation 1, and take outside the common factors, common terms, so not common terms, constant terms. Constants are q1 q2 and 4 5 epsilon naught, take them outside. Okay, and integrate 1 by r square. So we can, if we integrate 1 by r square with respect to dr, what do you get? Minus 1 by r we get. See, minus 1 by r written, and integration limits are r1 to r2. Okay, now change in potential. So here is what I am writing, at a different position. Point B is there, C there. From B to C we have to do. So at a B, the what at a B it is a potential energy UR1, at C UR2. Okay, so in the place of W, what is substituted? Change in potential energies substituted. Why? Because work can be stored in the form of any energy, either kinetic energy or potential energy. Kinetic energy means particle has to move continuously, but here not moving, only one point to another point changed, and again there it is in stationary, in rest position. So that means particle is not motion, so only potential energy present, that is change in potential energy is this one. And here these are also substituted, then we get this one, right? It is, and a minus term is there outside. Okay, so this minus term, why it is minus term, minus term is here minus term, when we it is actually changes r1 minus r2 we have tried, it is reverse, so that is why minus term is written. And if you substitute the minus term inside, then their position changes, r2 comes this side, r1 comes this side, so position changes. So finally we get this one. So potential energy at infinity, at infinity means r1 is at infinity, then potential energy at infinity is how much? 0. So that is why substitute this term as a 0, here also infinity, here also infinity, then we get it is 0 term, it is also 0 term, then what? This and this remains. Okay, only this and this can remain, and this is written as like this. In general, remove the 2 here and 2, the in general potential energy, it is a function of distance, is equals to 1 by 4 pi epsilon naught q1 q2 by r square. When we consider the two charges, then it is a formula. If we have the three charges, then what is the formula? U of r is equals to 1 by 4 pi epsilon naught 1 by r into q1 q2 plus q2 q3 plus, right, like this, q1 q3, like this, so many terms comes. So okay friends, thank you for watching this video.